Now we'll look at the solution to the fifth assignment. The first problem here is it's a control source, it's a source follower realized using MOS transistors. Now it has a bias current I0 which is substituted by a resistor R0 for biasing. Okay. So first of all, the first part of the question is this R out has to be 5 kilo ohms, and you know that the output resistance of a source follower is 1 by GM. This is 5 kilo ohms, so which means that GM is 200 microsiemens. And also for the given MOS transistor parameters, you can calculate that from this VGS minus VT has to be 2 volts, or the bias current I0 has to be 200 microamperes. Okay, so that's the answer to the first part, bias current I0. Now it says that it's actually implemented with a resistor in place of the current source, and the quiescent voltage across the resistor is 5 volts. Okay, then you have to determine the gain. Now across this we have 5 volts, and through this we have 200 microamperes, so R0 is 25 kilo ohms, 5 volts divided by 200 microamperes. Okay, and you can see that in the signal picture, first of all, R1 and R2 are very large, so we just neglect them, and C1 is large, so we short circuit them. So the signal picture looks like this. We have Vin going to the gate of the MOS transistor, and we have the control source GM VGS, and from here we have the biasing resistor R0, which is basically like the load resistor RL. This is 25 kilo ohms. Okay, so you know that the gain of the source follower V0 by Vi is GM RL by 1 plus GM RL. In this case it is GM R0 by 1 plus GM R0. Okay, and GM is 200 microsiemens, R0 is 25 kilo ohms, so GM R0 is 5. So V0 by Vi is 5 by 6 or 0.83. Okay, so this is 0.83. Now here is another control source. Basically it looks complicated, but you have to realize that all we have is M1 with source feedback biasing. The source feedback biasing comes from this current mirror M00 M0. That's all. Okay, and what is this control source? You can see that there is a resistance connected from the source of M1 to ground. So between Vi and this ID, it's a voltage control current source. Okay, and then we have an inductor, so that it's an open circuit for signal frequencies, and this load resistance RL, so that all of ID goes into that one. Okay, first of all, you're told that ID by Vi is 20 microsiemens. Okay, and you know that it's basically, this is the transistor that is implementing the voltage control current source. If its transconductance is GM and this resistance is R, then this is GM divided by 1 plus GM R. Okay, and R is given to be 45 kilo ohms. Okay, so now by solving this, you will find that GM will be equal to 200 microsiemens. Okay, because then 200 microsiemens divided by 1 plus GMR, 200 microsiemens times 45 kilo ohms is 9. So this will be 20 microsiemens. It will satisfy this equation. Okay, and you have to find the bias current I0, because it's the same bias current flowing through the transistor. You know that for GM of 200 microsiemens with these transistor parameters, you need I0 to be 200 microamperes. So the bias current I0 is 200 microamperes. Okay, and the next question says that if M0 is on the verge of triode region, that is, it just meets the condition for saturation, determine the ratio R1 by R2. Okay, so there is 200 microamps flowing here, and M0 is on the verge of triode region. What does it mean? It's VDS equals VGS minus VT, which is 2 volts in this case. So this point, this is at 2 volts, and the gate of M1, it is 1 VGS above this, because here we have VGS of 3 volts. So this is at 5 volts. Okay, and across R1 we have 7 volts, across R2 we have 5 volts. Okay, so what we have to find is the ratio R1 by R2, which is basically in proportion to the voltages, because the same current is flowing through them, which is 7 by 5 or 1.4. Okay, so this ratio is 1.4. The next question, it says that V0 by Vi is minus 4, and you have to find RL, assuming that the inductor is an open circuit and the capacitor is a short circuit, and so on. Okay, and this is actually quite easy, because we know that this ID, the small signal ID, is 20 microsiemens times Vi. Okay, and V0 is nothing but minus ID times RL. If L2 is an open circuit and C2 is a short circuit, all of it goes that way. Okay, and here you are given that V0 by Vi is minus 4. Okay, so V0, which is minus 20 microsiemens times RL times Vi, this is minus 4. So from this you will get RL to be 4 divided by 20 microsiemens, or 200 kilo ohms. Okay, so RL is 200 kilo ohms. And finally, you want to determine the condition on L2 so that it's an open circuit. We know that L2 has to be such that its reactance is much more than RL. So the idea is that all of the drain current, the incremental drain current, goes into RL and not L2. So omega times L2 has to be much greater than RL, or L2 has to be much greater than RL, which is 200 kilo ohms, divided by omega, and omega corresponds to 1 megahertz, which is 2 pi times 10 to the 6 radians per second. So this, if you evaluate, you will find that L2 has to be much greater than 32 millihenries. Okay, if you keep the decimal places, you will find 31.83 or something like that. Okay, so if you make L2, let's say 10 times larger than this, 320 millihenries or something more than that, it will behave like an open circuit. That is, all of the incremental drain current will go into the load resistor RL. The next question here, what kind of circuit is this? You can see, first of all, the transistor biased with source feedback biasing, and the input is applied to the source, the output is taken from the drain. So this is a common gate amplifier. Okay, and you can also see that the gate is incrementally grounded. Okay, so first you are told that the drain and gate voltages in the quiescent condition are equal to each other, and the source of the transistor is at 1 volt with respect to ground. So this one here, this is at 1 volt with respect to this ground. Okay, right, so with 10 volts and 6.4 and 3.6 mega ohms, we will have 3.6 volts here, and the source is at 1 volt, the gate is at 3.6 volts. So VGS is 2.6 volts, which corresponds to a current of 128 microamperes. Okay, so basically you are asked for the gain V0 by Vi. For that you need to know the small signal model, or the small signal parameter GM of the MOS transistor. Okay, so the GM of this is basically whatever corresponds to 128 microamperes. So GM will be 160 microsiemens. Okay, now if you write the incremental picture, we have the gate which is grounded, the drain which is going to RD and RL in parallel, and you're also told that RL equals RD. Okay, but neither RD nor RL is given. So how do you find the values? For that you use the condition that drain and gate voltages are equal to each other. So the gate voltage is at 3.6 volts, the drain is also at 3.6. Okay, so what do we get? RD is basically 10 volts minus 3.6 volts, that's the drop across it, divided by 128 microamperes, whatever value you get out of this. Okay, and RL is also exactly the same. Okay, so this RD, you will see that it is 6.4 volts divided by 128 microamperes, or 1 by 20 micro, or basically 50 kilo ohms, and RL is also 50 kilo ohms, so we have 25 kilo ohms there, and effectively 25 kilo ohms. And on the input side we have 10 kilo ohms in series with Vi. Okay, and this GM is 160 microsiemens times VGS. Okay, of course you can go and analyze this from scratch, but essentially you know that here V0 by Vi will be RD parallel RL divided by RS plus 1 by GM, which RD parallel RL we know is 25 kilo ohms and RS is 10 kilo ohms, and 1 by GM is 1 by 160 microsiemens, or 6.25 kilo ohms. Okay, so that's the gain, and it comes out to be 1.54. Okay, so the gain is 1.54. So there is some information that is given. So you're not given the complete small signal model and asked to calculate V0 by Vi, but some conditions are given, so which gives you some practice in circuit analysis. Okay, so first some operating point calculations from which you can calculate the GM and values of RD and RL and so on. Okay, so the next one, this is pretty straightforward. We have a current mirror biasing, but this also has an additional common gate stage here. You can think of M1 as a common gate amplifier. Its input is not from an input source but from this common source amplifier. Okay, so this is a common source amplifier and that's a common gate amplifier. Okay, but even if you didn't realize this, you should be able to write down the small signal picture and calculate everything that you need to. So first thing is to calculate V0 by Vi, but unlike the usual case where V0 is from drain to ground, here V0 is between drain and source. Okay, so you have to find the drain voltage, source voltage, and find the difference. Okay, so first of all you have to write the small signal picture. The gate of M1 is grounded, and this, the drain is terminated in 60 kilo ohms, and this is, let's say, Vd, and then this current comes from another MOS transistor. Okay, and at the input we have 195 kilo ohm and 100 kilo ohms and Vi. Okay, so this one I'll call it VGS1, though this is GM1 VGS1, and this one I'll call it VGS2. This is GM2 VGS2. Okay, and here we have a third transistor which is diode connected. Okay, now I'm not going to go through the details, you can refer to the lecture. Diode connected transistor looks like a resistance of 1 by GM, and in this case the current through all transistors is 200 microamperes, so the GM of all these three transistors is 200 microsiemens. So this one is 1 by 200 microsiemens, which is 5 kilo ohms. Okay, now you can immediately see that there is a voltage divider here, 100 kilo ohms and 200 kilo ohms. So the voltage at the gate of this transistor here is 2 times Vi by 3. Therefore this current is GM1 times 2 Vi by 3, and GM2 VGS2 is the same as GM1 VGS1, and GMs are the same, so VGS2 has to be equal to VGS1. So VGS2 equals 2 Vi by 3, which is also VGS1, the voltage between here and ground. So this voltage here is at minus 2 Vi by 3. Okay, and this current GM1 times 2Vi by 3 flows through 60 kilo ohms. So across this we have a voltage which is GM1, which is 0.2 millisiemens, times Vi by 3 times 60 kilo ohms with a negative sign because of the direction of the current. So this gives you minus 8 Vi. Okay. Now what you need is the difference between this and that. So that is minus 8 Vi plus 2/3 Vi, which gives you minus 7.33 Vi. So this V0 by Vi is basically minus 7.33. Okay. And let's say in the same circuit lambda is 0.05. So you have to find the small signal output resistance looking into the drain of M1. Okay. And that's not very difficult. When you calculate the output resistance, you disable the input source. We have the small signal model where the diode connected transistor is replaced by 5 kilo ohms resistor. We have 195 kilo ohm and 100 kilo ohm, and the input is set to 0, so that is grounded. And this is the gate of the first transistor on the right side, and this is GM1 VGS1. You can clearly see that there is no source here, so VGS1 is 0, so GM1 VGS1 goes away. It becomes an open circuit. All we have is the GDS of this transistor. And how much is GDS? Again, for operating point calculations, you ignore this effect of lambda. So GDS is nothing but lambda times ID, which is 0.05 times 200 microsiemens. Okay, so which is 10 microsiemens or 100 kilo ohms. And the next transistor here, the gate is grounded, so this is VGS2 and this is GM2 VGS2, and across that you again have a 100 kilo ohm resistor. Okay, so now what you have to do is to calculate the resistance looking in that way. Okay, this is R out, and this one, it turns out it's easiest if you do it with a test current instead of a test voltage. If you have I test here, this I test will go, it will split between these two, but finally the same I test will have to flow here because there is no other way. So this is I test and this is I test times 100 kilo ohms, and VGS2 you can see is nothing but minus I test times 100 kilo ohms, and GM2 VGS2 will be in this direction because of this negative sign, and in that direction it will be basically 20 times I test. Okay, so GM2 is 200 microsiemens that you multiplied by I test times 100 kilo ohms. Okay, so the total current here is 21 times I test. So the total voltage across this is 21 times I test times 100 kilo ohms plus I test times 100 kilo ohms. So the resistor comes out to be 2200 kilo ohms or 2.2 mega ohms. Okay, so that concludes the problems in the 5th assignment.